This is a short presentation about manifold exploration, which is a new way of dealing with specular paths in rendering. By a specular path, what I mean is the trajectory of a hypothetical light particle on its way from the light source to the camera such that it gets scattered by one or more materials like glass, water, polished metal, or anything with a smooth coating on top. There are many different types of these paths, and caustics are just one well-known example. If you've ever rendered a scene containing many of them using an algorithm like path tracing, you'll likely have run into convergence issues that manifest as excessive noise. This is a serious problem because these paths are everywhere, and they're quite important for accuracy even when they don't cause dramatic lighting effects. There are also many things that are near specular, like glossy wood or brushed metal, and these are really just as problematic. Now, the reason why these are difficult for unbiased rendering algorithms to handle is because they rely on generating many independent random samples, and so the only way that they can find these paths is by chance, and in some cases this happens with low probability. The goal of this project is to do something about the way that these paths are being found. We can start off with an observation, which is that paths containing a specular scattering event lie in a subset of the path space that has a lower dimension. In the flatland example below, you can see that for each pair of points on the emitter and receiver, there is actually just one point on the mirror that will transport light in between them, and this means that the actual set of paths is two-dimensional instead of three-dimensional. This can be interpreted as a constraint which states that the point on the mirror must always be halfway in between. On the right side, you can see a view of the entire space of paths that can connect points on the source and on the receiver. This view is abstract and only here for illustrative purposes. The axes don't really mean anything and just indicate path space. But what remains after applying the constraints due to the specular materials is a lower dimensional subset of paths that actually do carry some illumination. We name this the specular manifold. Now, when you're rendering a specular scene using an unbiased technique, you're essentially throwing darts at this manifold, which often doesn't work all that well. But suppose there was a way to explore this manifold systematically by moving around on it, then that could be a pretty powerful tool for building a better rendering technique. I'm now going to focus on this part for a bit, and later we'll take a broader look at how exactly it can be used in the context of rendering. Since different spaces are being used in this talk, you'll occasionally see an icon to point out which particular one is being shown. I'll focus mostly on 2D, but the generalization to 3D poses no difficulties. Here's an outline of the talk. It's split into two parts, where the first one focuses mainly on the theory of specular paths, and the second is about applications to rendering. Let's start by taking a look at what other people have done about this problem in the past. In 1992, Mitchell and Hanrahan presented a technique for rendering reflections from implicitly defined surfaces. And more recently, Walter et al. Proposed a technique for rendering single scattering in objects with triangle mesh boundaries. Both of these projects had to solve an extremely difficult global search problem. The reason why it's global is because in theory any part of the geometry might add specular path to some other place. This means that these techniques are unfortunately infeasible for multi-bound specular interactions, they're restricted to certain types of geometry, and they don't work for rough surfaces. There's an interesting related paper by Chen and Arvo who derived second-order expansions of the neighborhood of a path to efficiently render approximate specular interreflection effects using hardware rasterization. The project that I'm presenting also relies on this idea of the neighborhood of a path, but it instead pursues the creation of a complete and unbiased global illumination rendering technique. Let's go back to this constraint idea from earlier and define it a bit more formally. From geometric optics, we know that when we're looking at a specular reflection from a smooth mirror, the inclinations of the two rays have to match. Mathematically, what this means is that the half-direction vector has to match the surface normal. Interestingly, it's almost trivial to extend this to the case of refraction, and the idea here is to weight the two directions by the corresponding indices of refraction, and this is just a neat way of encoding Snell's law. Now suppose we've got a light path with several such interactions. For instance, light that refracts into a glass of water and out of it again. Each interaction will add a constraint, and then if we take all of those constraint equations and stack them into a vector-valued function, then we can think of the set of valid light paths as the set where some function c equals 0, and so now c contains all of these constraints. This looks a lot like an implicitly defined surface, except that the ambient space is now path space instead of R3. Now, whenever we come across something that's implicitly defined, there's a great tool for that, which is the implicit function theorem. And just to remind you what that states is that under relatively mild conditions, there exists a local parametrization of the manifold, and we can easily also find the associated tangent space by computing derivatives of this function c. These tangent vectors are key to our method because they enable us to locally explore the manifold as part of our rendering technique. Let's focus on a more concrete example. This is a path that refracts through a glass sphere, reflects off the mirror, and then goes back again. It's a chain of 5 specular vertices with 2 non-specular endpoints x1 and x7. By differentiating the set of constraints associated with this path, we get a tridiagonal matrix, and the reason for that is that each specular constraint only depends on the current and the neighboring vertices. We can now use the implicit function theorem to find the manifold tangent vectors. For instance, we can compute the derivative of all specular vertex positions with respect to the endpoint x7, which turns into some fairly basic linear algebra. And here's a visual demonstration of these tangents. I can take this endpoint x7 and move it around and get a linear approximation of all the other vertices. Due to the special structure of this matrix, all of the computation that's necessary to compute tangent vectors is linear in the size of the path, so it scales up nicely. So this is kind of neat, but it's not all that useful on its own, because we're only changing the path according to a first-order approximation. We need some way to get back onto the underlying manifold, and it happens to be that there's a really simple way to do that called ray tracing. The idea is to just retrace this linearly extrapolated path. The details are in the paper, but suffice it to say that this ends up being a projection operation. Now if we put together both of these pieces, the extrapolation and the projection, we end up with the manifold walking algorithm. It behaves like Newton's method and has quadratic convergence close to the solution. Note that this is an entirely local method, and therefore it avoids the complexities of a full global search. And here is a visual demonstration of this algorithm for the same scene. I can now move one of the vertices, and then the entire path is updated so that it remains in a valid specular configuration. This is really a new kind of operation in graphics that wasn't available before. And even for these very long paths, with for instance 23 specular interactions on the left side, the algorithm still converges to machine precision within just 2 iterations. Before we continue to the application part of the paper, I want to say a few words about the underlying integration problem. When computing the intensity of a pixel j using the path space framework, we compute an integral over all light paths where the integrand is this somewhat messy expression. Most of these terms are just mathematical descriptions of the light sources, the cameras, and the materials in the scene. But let me draw your attention to the remaining ones. These are the so-called geometric terms. And these capture the derivative of the projected solid angle at one vertex with respect to area at the other end. One interesting question is what path space integrals should look like when specular interactions are involved. The short answer is that nobody knows. This is usually something that is sidestepped in the transition from theory to implementation. Part of the difficulty, it turns out, is coupled to these geometric terms. When a path contains a series of specular scattering events, such as refraction through this glass egg, we require a new kind of geometric term that captures the derivative of projected solid angle through the entire chain and with respect to area at the far end. This generalized geometric term can be computed from the block tridiagonal matrix we saw earlier, and with that it becomes possible to write down proper integrals over these spaces. But let's go back to the bigger picture. Using derivatives of a path, we were able to construct a method that could move from one point to another on the specular manifold. And we looked at a generalized geometric term that became necessary when computing path space integrals involving specular materials. We think of the theory as a really important part of the paper, but now I'll also tell you about how to turn these tools into a working rendering technique, and for this we rely on Markov chain Monte Carlo. There have been several methods that rely on this approach in the context of rendering, starting with the seminal Metropolis light transport algorithm proposed by Veach and Guibas in 1997. Kellerman et al. Created a simplified variant of MLT that explores the space of paths by perturbing the random numbers that are used to generate them. And Klein et al. Proposed energy redistribution path tracing, which combines aspects of MLT with path tracing. Manifold exploration also fits into this general class, and we'll later compare against these techniques. Here's the basic pseudocode. This is an iteration that starts with some path, and then for a number of iterations does the following. A change is performed to the path, which could be a small perturbation or a large-scale change. In our case, that change is done by generating a new path on the manifold that lies in the neighborhood of the old path. The result is called the proposal path, and that proposal is either accepted or rejected randomly based on some probability that's coupled to how the change was made. And finally, the contribution to the output image is recorded. I will focus on the mutation because this is the most interesting part. Let's look at how this works in our case by way of an example. Suppose we start with a path like this. Through a mirror, the observer is looking at a diffuse surface on which a caustic is being cast. One sensible way to change this path is by slightly adjusting the outgoing direction at the observer, and after propagating this direction through the mirror, we end up with a vertex on the diffuse surface. And now the question is, how can we connect this point to the light source when there is a specular object in the way? Previously, you just couldn't do it, at least not exactly. But now we can set up a specular manifold and search the neighborhood of the old path to find a new one that has the connection we want. There's also one neat aspect of this approach that I didn't mention yet. In general, all of the things that we talked about so far only apply to perfectly smooth mirrors, polished glass, and so on. But if we wanted to render rough glass instead, then it appears that we just cannot do it with this method. But it turns out that there's an almost trivial generalization that also allows us to handle roughness. The underlying idea is that in the perfectly smooth case, there is one path connecting these points here, and in the manifold case it means that all of the energy is concentrated on the specular manifold. But if one of the surfaces is rough, then there is a whole family of paths that connect these 2 points. And in the path space view, it means that the energy is now concentrated on a thin band that is centered around the manifold. What we do is to think of this as a family of offset manifolds with different constants, and in that case it turns out that we can use all of the existing machinery to walk parallel or perpendicularly along these offset manifolds to explore the entire space. All of this also generalizes to volumes. In the paper we show that from a mathematical standpoint, anisotropic volume scattering events are not unlike specular interactions with surfaces. Here you can see a screen capture from a rendering session with our system. The little squares are where Markov chains are being started, and you can see how they explore their respective neighborhoods. This new perturbation can be used in different rendering frameworks, including Metropolis light transport and energy redistribution path tracing. I'll only present ERPT results since this version works slightly better. We call the resulting algorithm Manifold Exploration path tracing. It's implemented in C++ as a plugin to the Mitsuba renderer. I'll now show comparisons against several state-of-the-art algorithms, specifically against the set that you saw earlier: Metropolis light transport, primary sample space MLT, and energy redistribution path tracing, and these are referred to as MLT, PSS MLT, and ERPT. To test this new rendering technique, we created a scene that's meant to be extremely difficult for unbiased rendering algorithms to handle. What you see here is a rough brass chandelier with 24 glass-enclosed bulbs, and so that means that any visible light here is via caustic paths. All of the techniques we investigated can render these scenes and arrive at the right answer eventually, but we only allocated 1 hour to each one, which is not enough for any of them to converge. Primary sample space MLT creates a rendering that's relatively noisy. MLT is missing many light paths due to some inherent limitations of the bidirectional mutation that are discussed in the paper. ERPT does quite well, but there are still some bright pixels, for instance, on the door, and it doesn't do well on some of the rough interreflection paths. MEPT also does well, and it gets rid of the bright pixels on the door. And here again is the fully converged reference image, which was rendered with MEPT for about a day. Here's a rendering of tableware that's actually lit by the chandelier that you just saw. So just to emphasize, not only are we looking at glossy reflective and refractive objects, but they are also illuminated entirely through caustics. PSS MLT creates a rendering that is extremely noisy. MLT produces an overall smooth result, but it's missing many of the truly difficult light paths in this scene. When it occasionally finds one, it explores it for a long time, which creates visible artifacts. ERPT does better at finding the difficult light paths, but it cannot explore them well. MEPT can find and explore these paths, and it's still a bit noisy after 1 hour, but after 24 hours, this is the image that you get. And finally, here's another view of the same scene now lit from outside through windows. It also contains a glass egg with an anisotropic volume inside. PSS MLT is doing okay, but the result is still quite noisy. The other techniques have real problems with the media and glossy surfaces. Our method produces an almost converged image after 1 hour. And here again is the converged reference image. I've presented Manifold Exploration, which at its core is a fundamentally new way of thinking about specular paths. For the first time, we have a method for systematically exploring paths in a general setting and without having to solve a difficult global problem. This theory translates into a practical rendering algorithm that can handle very challenging scenes favorably. And despite starting out with a specialized analysis of simple light paths with perfectly smooth materials, we ended up with a technique that can handle essentially any kind of transport. One limitation of the current scheme is that it needs seed paths to start the Markov chain iteration. Right now these are created using bidirectional path tracing, which means that the more difficult the input, the harder it also becomes to find them. The nice thing about this method is that you only have to find each island of paths once, but you still have to find it. This is something we want to investigate in the future. Also in the future, it would be great to look at further extending the usage of derivative information in rendering. We have shown a way to incorporate this information, but there could also be many other applications of these ideas. It'll be interesting to see what kinds of questions can be answered by them. We thank our funding agencies and Olesier Zanko, who modeled the example scenes that were used in the paper. All of the code is available at the address listed below. Apart from Manifold Exploration, it also includes implementations of some of the prior work, particularly energy distribution path tracing and Veach-style Metropolis. If you're interested, I encourage you to download it and give it a try. Thank you very much for listening.